So the most important point when we're talking about the speed of a wave is that waves travel at a constant speed. So for anything that travels at a constant speed, what we've seen is I can figure out what that speed is by knowing the distance that it travels and dividing by time. If I figure out, well, what's the distance my wave travels in meters and divide by the time it takes to travel that distance in seconds, then I'm going to get the speed of the wave in meters per second. For a wave, of course, there happens to be a special distance and a special time. The special distance for a wave is how far that wave has to travel to complete the cycle. So how far does the wave travel before it starts to repeat itself? That's the wavelength. The special time for a wave is how long does it take for the wave to start to repeat itself. So that's the period. It's the time the wave takes to complete one cycle. So another way that I can calculate the speed of a wave, d over t works, distance over time works, but wavelength over period will also give me the speed of a wave. 1 over t is equal to the frequency. So what we'll often do, instead of writing the speed of a wave as wavelength over time, we will tend to write it as frequency times wavelength. So this is the most common equation for calculating the speed of a wave. If you go look up parameters for various waves, what you'll look up are what frequency values are appropriate for some type of wave, and then what wavelength values are typical for that type of wave. To be clear, the frequency is in hertz. The angular frequency is in radians per second, and that's what we plug into our wave equation. This f is the frequency, and that's just 1 over seconds, or hertz. Equation number 2 for calculating a wave, speed equals frequency times wavelength. Well, of course, I can also take the wavelength and the period, and I know that those are related to k, my angular wave number, and omega, the angular frequency of the wave. And so 2 pi over t, that's omega. 2 pi over the wavelength, that was k. So if I've got this flipped over, so this is the wavelength over 2 pi, that's got to be 1 over k. So basically all I've done is I took this, split it apart, and also multiplied by an interesting variation on the number 1, 2 pi over 2 pi, and put a 2 pi with the t and a 2 pi with the wavelength, and what that gives me is omega times 1 over k. So the last way that I can calculate the speed of a wave is omega, the angular frequency, divided by k, the angular wave number. If you're given a plot of the disturbance of the wave, that the displacement as a function of position and the displacement as a function of time, how can you use those two graphs to figure out the equation of your wave? I still need to be given two plots, but here what I'm given is not one of position and one of time. What I'm given is two plots of position and then two curves that represent the time. So the red curve here is where the wave is at t equals 0. The blue curve is where the wave has traveled at t equals 2 seconds. And so again, I can use these two plots to figure out the equation of my wave. So same thing as before, I can read off the amplitude because position on the horizontal axis. I can read off the wavelength, and then I can read off the phase shift. The other piece of information that I can read off of this plot is the distance that the wave travels in whatever this difference between time is. So in this case, what I see is that the wave travels 0.4 meters, that's the distance measured along the horizontal axis here, in 2 seconds. So there are now again two calculations I can make. One is I can take my wavelength value to calculate out k. The second one is I can take my distance measurement and the time I know to calculate the wave speed. So if it travels 0.4 meters in 2 seconds, that means the speed of this wave is 0.2 meters per second. Once I know k and the speed, I can then calculate out omega. So we said that the speed is equal to omega over k, so I'm simply solving that equation for omega, and I get that omega is equal to the speed times my angular wave number. The angular wave number we said was pi. The speed we said was 0.2. Multiply those two things together and I get 0.2 pi radians per second. Now I know amplitude, phase shift, wave number, angular frequency. So I can plug all that in to my wave equation. The equation that describes my wave as it's plotted here is 4 sine, and then inside my phase is pi x minus 0.2 pi t plus pi over 2 for the phase shift. The speed of a wave depends on the medium through which it travels. So part of our saying that the speed of a wave is constant means that we're making an assumption that the medium it travels through doesn't change. And we will talk about some situations in which we relax that assumption. But for most things, that's a pretty good basic assumption to start with. So the speed depends on the medium through which it travels, which means that we can come up with a couple of special cases where we can calculate out what the speed of a wave is based on physical parameters of what that wave is traveling through. So the first of these, if we have a wave traveling on a string. Notice that the speed of a wave for a wave on a string is equal to the square root of two things. The first is the tension. What's the tension in the string? The second, this mu, is the linear mass density of the string, which is another way of saying mass per length. So the linear mass density just says, well, it's a density, but because all of your mass lies along a line, instead of being mass per volume, which is the way we tend to think about a density, it's mass per length, because that's all you have. Basically, all your mass is smeared out in a single line. It makes sense, right? If the speed of a wave depends on a medium, it makes sense that the speed of a wave on a string depends on the parameters that define what's going on with the string. So you can think about, the easiest way to think about this is, say, a guitar string. You can change the tension of a guitar string. Different guitar strings have different masses, even though they tend to be roped off to the same length, they have different masses. So that means they have different linear mass densities. Over the 6 strings on your guitar, the waves travel at different speeds through those strings because you've changed what the physical parameters of the strings are. So this is one way that we're going to be able to calculate the speed of a wave, of a mechanical wave, given physical parameters. The other one that we'll deal with is calculating the speed of sound in air. The medium that sound travels through in air is obviously the air molecules. They're bouncing back and forth, and as they vibrate, they bounce into each other, and that bouncing into each other again transfers energy that then is that those particles continue to bounce back and forth off of the next ones. That's how that energy is transferred when you think about sound. And as you change the air temperature, you're changing the properties of the air. Changing the property of air changes the speed that sound travels through it. So we'll calculate out the speed of sound by basically saying it's going to be 331.3 meters per second times the square root of this additional term, 1 plus the air temperature in degrees Celsius divided by 273.15. So this gives us two ways in which we can talk about the physical parameters of the medium and use that to calculate the speed at which waves will travel through that medium.